Good morning, dear students. Today we are going to solve October-November 2012 2-1 paper. It's a theory paper. The syllabus we are studying is Physics 5054. My name is Ferhan Mazher. In this video, we will solve only the section A of this paper. Let's start. A parachutist of total weight 950 Newton falls vertically at a constant velocity of 6.5 meter per second. State the size and direction of the resistive force acting on the parachute. You see, the weight of the parachutist is given 950 Newton and he's falling with the constant velocity. When he's falling with the constant velocity, we call it terminal velocity, and we know that the constant velocity is only possible when the upward and the downward force are balanced with each other. The acceleration is zero, resultant force is zero, and the downward force is the weight of the body, and the upward force is the air resistance. So the in this situation, it means that the air resistance will be equals to the weight of the body. So the size of the resistive force will be 950 Newton. So here we will write 950 Newton. Then he says direction of the resistive force. Direction of the resistive force is opposite to the motion of the body, because the body is falling downward. So the direction of the resistive force will be upward. So here you will write upward. I hope that you have understood. B part, at a certain height, the wind starts to blow and the parachutist moves horizontally at a velocity of 4.5 meter per second as he continues to fall. Use a graphical method to add together the horizontal and the vertical velocities to determine the size of the resultant velocity of the parachutist. Label the velocities and state the scale that you use. You see here we have two vectors. One vector is 4.5 meter per second velocity and it is horizontal. The other vector is the velocity of the falling parachutist, that is 6.5 meter per second, and it is acting downward. Both these vectors are at 90 degree to each other. One vector, which is 6.5 meter per second, is acting downward, and the other vector is 4.5 meter per second and it is acting horizontally. So the angle between them is 90 degree. To find their resultant, we will apply the parallelogram law. And in the parallelogram law, if you want to find the resultant of two vectors to be added, what we do, we put both the vectors in such a way that their tails are joined together. And once we have put them in such a way that their tails are joined together, then we suppose that these two are the adjacent sides of a parallelogram. And then we complete the parallelogram. And then what we do, we join the point where the tails are together with the opposite corner of the parallelogram. And that diagonal is equals to the resultant force. So first of all, we have to choose a certain scale. For example, one velocity is 4.5 meter per second. The other velocity which we have to represent graphically is 6.5 meter per second. So let's say if you can choose, maybe you choose that 1 meter per second is represented with 2 centimeter. If you choose this scale, then 6.5 meter per second will be represented with 13 centimeter, and 4.5 meter per second will be represented with 9 centimeter. I have drawn this on a paper. Let me. Okay, dear students, so we are back. Due to internet connectivity, there was a problem. So I'm back again. Okay, so I was telling you that we have drawn that vector diagram on a paper. The scales I have chosen are 2 centimeter will be representing 1 meter per second. The horizontal velocity was 4.5 meter per second. So here I have represented it with a length of 9 centimeters. The vertical velocity, which was downward, was 6.5 meter per second. And I have represented it with a length of 13 centimeter line. And the angle between these two is 90 degrees because this is horizontal and this is vertical. Then we will suppose that these two lines, these two vectors, they are the adjacent sides of a parallelogram, and we will complete the parallelogram. So parallel to this 13 centimeter line, I will draw here a line 13 centimeter. And parallel to this 9 centimeter line, I will draw a line here which is of 9 centimeter length. So my parallelogram will be completed, and then I will join the point where the tails of the vectors to be added. Their tails were joined with each other. I will join that point with the opposite corner of the parallelogram. That will be the resultant. So I will measure this. This will be approximately 16 centimeter, and 16 centimeter means 8 meter per second. So the size of the resultant velocity is 8 meter per second, and the scale we have chosen is 2 centimeter representing 1 meter per second. It was a 3-mark question. You have to actually draw this. So actually draw this on a paper, and when you will draw this, you will understand it better. I hope that this is clear to you. Okay, now we are moving to the next question, and next question on your screen. Here we have the next question. A thermocouple thermometer is made from 2 different metals and a voltmeter. One junction of the thermocouple thermometer is placed in a beaker containing a mixture of water and ice. The other junction is placed inside a high temperature furnace as shown in the figure 2.1. The thermocouple is okay. The thermocouple thermometer has a linear output over the operating temperature range of the furnace. State what for a thermocouple thermometer is meant by a linear output. Linear output means that there is a equal change in the EMF produced for equal rise in the temperature. You know, in the thermocouple, here we have, normally this is of copper, and this wire is made of iron. Here we have connected a voltmeter. This is called the cold junction, and this is called the hot junction. And when there is a temperature difference between the cold junction and the hot junction, naturally or automatically, by the laws of the nature, what happens, EMF is induced, and that EMF is shown by the deflection on the voltmeter. So whatever is the reading on the voltmeter, that gives you the an idea that how much EMF is produced. The greater the temperature difference between the cold junction and the hot junction, the greater will be the EMF on the voltmeter. And if the temperature difference between the hot junction and the cold junction is less, so less EMF will be shown on the voltmeter. So here the voltmeter reading is an indicator of the temperature difference between the cold junction and the hot junction. So he says that the output of this thermocouple is it has linear output. Linear output means that for equal change in the temperature or equal difference in the temperature, the reading on the EMF is same. Okay, so I have written this answer also. Let me show you my answer, written answer here. So he says change in the EMF on the voltmeter is directly proportional to difference of temperature between hot and cold junction of the thermocouple. So the reading on the voltmeter is directly proportional to the temperature difference between the hot and the cold junction. So the directly proportional thing means that they are linearly related. Okay, so the next question is, it was a 1-mark question. The next question, little bit tricky question. He says the junction inside the furnace is at a temperature T. Figure 2.2 shows the reading V of the voltmeter at two values of T that are within the operating temperature range of the furnace. So when inside the furnace the temperature is 750, the reading on the voltmeter is 6.2 millivolt. And when the temperature inside the furnace is 800 degrees centigrade, the reading on the voltmeter is 7.70 millivolt. When the furnace is operating at high temperature, the furnace door is open and the reading on the voltmeter falls to 6.80 millivolt. Calculate the temperature of. So let me share the screen again. Hello. So we are back due to internet connectivity. You know, there are problems. So we are back again. He says when the furnace is operating at a high temperature, the furnace door is open and the reading of the voltmeter falls to 6.80 millivolt. Calculate the temperature of the junction inside the furnace. Okay, so the temperature is question. So I have done this on, you can see that when the temperature is this, the voltmeter reading is this. When the temperature is this, the voltmeter reading is this. When the voltmeter reading is 6.80, what is the temperature? That is the question. So let me take you to the, I've done this and okay. So here we go. Let me increase the size so you can see it more clearly. So here we see. So here we have a formula which we use for the, you know, when T3 minus T1 divided by T2 minus T1 equals to EMF3 minus EMF1 divided by EMF2 minus EMF1. T3, we want to find out that temperature. On T3, the EMF reading is 6.80. T1 is 750. The EMF reading is 6.20. And when T2 is 800 and the EMF2 is 7.70, T1 is 750 and its value is EMF1 is 6.20. Just do the calculation and you get the value of T3, that will be 770 degrees centigrade. It's a little tricky question. I hope that you have understood it. It's okay. So we are moving to the next question, and the next question says, it says, state state why a liquid in glass thermometer is not used to measure the temperature inside the furnace. You see, the temperature inside the furnace is very high. The glass of the thermometer will melt at that temperature. So we cannot use the glass, liquid in glass thermometer here. I have written this answer. Let me show you my answer also. Okay, here you go, B part. At this high temperature, glass will melt. The glass of the thermometer will melt. Okay, so we cannot use the liquid in glass thermometer inside the furnace because the temperature inside the furnace, you can see, is 770 degrees centigrade. It's a very high temperature. At this high temperature, the glass of the thermometer will melt. So you cannot use it. Okay. Next question. Let's reduce the size a little bit so you can see the whole figure. Figure 3.1 shows an electric motor being used on a building site to lift bricks. So here we have the electric motor. The height is 2.8 meter, and this motor, by using this, here we have a pulley, and this is lifting these bricks to this platform. This platform is 2.8 meter high. Okay. The gravitational field strength is 10 Newton per kg. The motor lifts bricks of total mass of 54 kg through a height of 2.8 meter in 3 seconds. Calculate the work done in lifting the bricks. The work done when you lift something vertically upward can be found by the formula weight multiply height, or you can apply the formula mgh. Okay, so mgh, and you know the m value is 54 kg into 10 into 2.8, so the answer is 1512 joules. This is the work done, mgh. In the second part he asked that how much is the power. You know the power is work done divided by time, and the work done is 1512 joules, and this was done in 3 seconds. So divide the work done with the time taken, and the answer will be 504 watt. So the first question was the work done in lifting the bricks, and here we have the mass of the brick. We know the value of the g, and we know the height. So the mgh, and that was a 2-mark question. Then the next question, it was also 2 marks. He said the useful output power of the motor. I just shown you the answer. The power is equal to work done divided by time. The work done you just calculated, and the time taken is 3 seconds. Just divide that work done with 3 seconds, and you will get the answer, and the unit will be watt. So just 2 reasons why the electric power supply to the motor is greater than its useful output power. Okay, so the power which you provided, the electric power you provided, and the power which the motor shown by doing the work, the electric power will be greater. Obviously, that's input power, that is always greater. The reason could be different. There might be, you see here, the motor has to lift the weight of this platform. The motor has to lift the weight of the rope also. The motor, there may be friction in the axle of the electric motor. Due to that, what will happen? The energy will be converted into heat. So there will be a loss or waste of energy. So I have written this answer also. Let me show you. Motor is also lifting the board on which the bricks are placed, and friction in the axle of the motor. These can be the 2 reasons due to which the sum of this power is wasted. Okay. Here we move to the next question. He says, figure 3.2 shows a battery and an electric motor. The battery used to power the motor. Complete figure 3.2 to show the circuit diagram of a circuit that is used to determine the power supply to electric motor. So what we will do, if you want to calculate how much is the power, the formula for the power is equals to IV. So I need to know how much current is flowing in the motor, and I need to know how much voltage drop is across the motor. So what I will do, I will connect it here, and I will connect a ammeter here in series with the motor, and I will join these two, and parallel to the motor, I will put a voltmeter. So you see, voltmeter will give me the voltage drop across the motor, and the ammeter will tell me how much current is flowing through the motor. So these 2 instruments, ammeter and a voltmeter, ammeter should be connected in series, and the voltmeter should be connected parallel to the motor. So I have drawn this diagram. Let me show you my diagram here. Question number 3, see first part. You see here we have connected an ammeter. Ammeter is connected in series with the motor, and here I have connected a voltmeter, and the voltmeter is connected parallel to the motor. The voltmeter will tell me the voltage drop across the motor, and the ammeter will tell me the current flowing through the motor. Okay, it was a 2-mark question. State how the power supplied is calculated. The formula of the power is equals to IV. So what I will do, I will take the reading on the ammeter, and I will note down the reading on the voltmeter, and I will multiply them with each other. Multiply the value of the voltmeter with the value on the ammeter. Formula we use is power is equals to IV. Very simple question. A petrol tanker has a mass of 2,800 kg when empty and holds 30 meter cube of petrol when full. The density of the petrol is 740 kg per meter cube. And calculate the total mass of the tanker when full of petrol. You see here, the volume of the petrol is given 30 meter cube, and the density of the petrol is also given, that's 740 kg per meter cube. And he want us to find out or calculate the mass of the petrol. Density is equals to mass divided by volume, and the mass is equals to density multiply volume. So what I will do, I will take the reading. The density is 740, multiply it with the volume 30 meter cube, and the answer you will get is 2.2 into 10 raised to power 7 kg. I've done this on a paper also. Let me show you my work. So here we go. The density is equals to mass divided by volume. The petrol mass will be equals to density multiply volume, 740 multiply 30, and the answer will be 2.2 into 10 raised per 4 kg. So this is the mass of the petrol. His question is, what is the total mass? The total mass will be the mass of the empty lorry plus the mass of the petrol. So add these two masses, and you will the final answer will be 25,000 kg. So it was a 2 marks numerical where you have to find out the total mass of the tanker when full of petrol. Okay, so we found the mass of the petrol, and we also have the mass of the tanker. And then at the end, what I did, I added the mass of the tanker and the mass of the petrol, and I got 25,000 kg was my final answer. It's a 2 marks numerical. I hope you have understood. The full tanker is traveling along a road when the driver observes an obstruction and applies the brakes. A resultant force of 30,000 Newton acts on the tanker. Calculate the deceleration of the tanker. We know the resultant force, that's 30,000 Newton, and we also know the total mass of the loaded oil tanker, and we can find the acceleration or deceleration, you can say. F is equals to ma, Newton's second law of motion. F is equals to ma. A will be equals to F divided by m. So 30,000 divided by 2.5 expo 4, and my answer will be 1.2 meter per second square. Let me show you my work. I have done this on a paper. Okay, so F is equals to ma, A is equals to F divided by m, 30,000 divided by 2.5 expo 4, and the final answer will be 1.2 meter per second square. I hope that this is clear to you. So here we have, okay, a water wave of frequency 3.6 hertz is generated in a ripple tank. The frequency is given 3.6 hertz. Figure 5.1 is a scale diagram. Remember this word, scale diagram. So you can use a scale here, and with the help of a scale, you can measure the wavelength directly from this diagram. You can measure the wavelength with the help of a scale. Okay. Figure 5.1 is a scale diagram that shows the wavefronts traveling from deep water to shallow water in the ripple tank. A length of 1 centimeter on the diagram represents 8 centimeter in the ripple tank. Okay. So scale is 1:8. It means 1 centimeter here. So for example, if you want to find out what is the wavelength, so measure what is the wavelength, this wavefront and this wavefront. Check how much is the distance between one wavelength and the next wavelength, and then simply multiply it with 8, and you will get the wavelength. Okay. Using measurements from figure 5.1, determine the wavelength of the wave in the deep water. Okay. So in deep water, what I will do, this see how many waves are there? 1, 2, 3, 4, 5. So there are 5 wavelengths, wave fronts, and 5 waves basically. So I will measure this distance, this whole distance, and then I will divide it with 5 to find one wavelength, and I will multiply with 8 because of the scale. I've done this on a paper. Let me show you. So the total distance is 6.85 centimeter in those 5 wavelengths, and so one wavelength will be 1.37 centimeter, and because of my scale, one centimeter was representing 8 centimeter. So 1.37 multiply 8, and the final answer will be 10.96, which is approximately 11 centimeter. So the wavelength is 11 centimeter. If you have a hard copy of this paper in front of you, use your scale to find the wavelength. Okay, it was a 2 marks question. The second part is calculate the speed of the wave in the deep water. We know the frequency of the wave, we know the wavelength of the wave, we can find the speed of the wave. The formula you know is V is equals to F lambda. V is equals to F lambda. So V is the question, F is given, and the lambda is also given. Just put those values. You will get your answer will be centimeter per second. So here I have done this on your screen. I hope you can see that V is equals to F lambda. V is equals to 3.6 multiply 11. The final answer is 339.6, which is approximately 40 centimeter per second. So this is the velocity of the wave in the deep water. I hope you understand. Okay. The next question is, as the wave passes into the shallow water state, what happens to the frequency and the speed? You know, when the water waves, they will enter in a shallow region, and their frequency will be unchanged. The frequency will not change. It will remain the same. The speed will decrease. The wavelength will also decrease. Here the question is about the speed. The speed will decrease. Frequency will be unchanged, speed will decrease. I hope you have understood. Here we go. Next question. Figure 6.1 shows part of a page from a pupil notebook. And so he's noting down the electromagnetic spectrum, and he's writing them in increasing wavelength. Okay. So you remember that code word we use is Ronald McDonald is very ugly except Gary. So when you look at here, Ronald McDonald, here you should have a microwave. And then you should have Ronald McDonald is. This microwave is on the wrong position. It should be here, and infrared should be here. Here, then we should have a visible light. Ultrasound is written here. Ultrasound is not a part of the electromagnetic spectrum. Ultrasounds are sound waves. They are not electromagnetic waves. They are not part of the electromagnetic. Here you should have ultraviolet. Here we should have ultraviolet, then X-rays, then gamma rays. Ronald McDonald is very ugly except Gary. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Remember this code word. Ronald McDonald is very ugly except Gary. List 3 errors in the pupil's notes. We have to note down 3 errors. So here, the ultrasound is not part of the electromagnetic spectrum, so the ultrasound should not be here. Here we should have, this is the first mistake, the ultraviolet is not written here. It's the second mistake. The infrared should be before the microwave should be here, and the infrared should be here. So the visible light is also not shown here. So there are 4 or 5 mistakes. You only have to mention there are 3 mistakes. Let me show you. I have written also this answer. He says that the I have noted down three mistakes here. Ultrasound is not part of electromagnetic spectrum. Ultraviolet is missing. Visible light is also missing here. So these are the three mistakes. He asked us for three mistakes. The mistakes are more. Hope you have understood. Okay. State and explain one application of X-rays in engineering. X-rays are used to find the cracks inside the metals. If you have a piece of metal and inside that metal piece we have a crack, then X-rays and you look out from outside, you will not be able to tell that there is a crack inside the piece of metal. But if you are using the X-rays, you can tell that the X-rays will help you to find out that there is a crack inside that metal piece. I've written this answer. Let me show you my answer. Okay, little lengthy answer. X-rays are used to detect cracks in metal. An emitter emits X-rays and they are passed through metals. On other side of metal, photographic film is placed or a detector is placed. If metal has crack, intensity of the X-ray will be more by detector when cracks come in front of the X-ray emitter. You see? So by this way, you will be able to tell that there is a crack inside the metal. I hope that you have understood. You can also check this answer from your textbook. In your textbook also, Physics Matters, or if you have another book, you will application of the X-rays. From there, you can write this answer also. This was question number 6. Now we are moving to question number 7. Figure 7.1 shows a solenoid made from wire wound around the plastic cylinder. Okay, so here you have a plastic cylinder and you have wound a wire around this, and here you have connected it with the positive terminal. Here you have connected with the negative terminal. So the current will flow from here, and from this side the current will go down and up. From this front side it will go down. So the question is, the current in the solenoid produces a magnetic field. Figure 7.1, draw the pattern of the magnetic field lines inside and outside the cylinder. Okay, so it's a 2-mark question. You know, this will, when the DC current will flow, when the DC current will flow through this, and there will be a magnetic, this solenoid will become electromagnet, and it will behave like a bar magnet, and it will have its north pole and its south pole, and it will have magnetic field around it. It will have its magnetic lines which will be coming out of the north and going into the south. Let me show you. I've done this on a paper also. Let me show you my diagram. So here we go. So figure 7. Question number 7, A part. So you see the current is coming from here and going like this, going like this, going like this. So if you, how you will decide that which end it will be the north and which end will be the south? The law is very simple. We have a right hand rule for the solenoid. Right hand rule for the solenoid. So what you will do, you will take your right hand. Remember my words, take your right hand and hold the solenoid in such a way that your fingers, they are in the direction of the current. So if I will hold the solenoid in this way, because from the side of the solenoid towards me, the current is going down. So my fingers are going down, and my fingers are in the you know in the direction of the current. So my thumb is pointing towards the north. So if you actually hold the solenoid in your right hand in such a way that your fingers are in the direction of the current, then your thumb of the right hand will be pointing towards the north. So this end will be north, that end will be south. So from here, the magnetic lines will be coming out, and they are going into the south. From here, the magnetic lines are coming out and going into the south. Magnetic lines are coming out and they are going into the south. And another way of deciding that which side of the solenoid will be which pole is if you look at this face. If you look at if you look at this face of the solenoid, and you observe that the current is rotating in an anti-clockwise manner. If you look at this face of the solenoid, and you observe that the current is flowing in a anti-clockwise manner, anti has an N, anti-clockwise manner, then that end of the solenoid will be a north pole. And if you look at this, you bring this in front of your face and you look towards this end of the solenoid, and you observe that the current is flowing in a clockwise manner. Then that side of the solenoid will be the south pole. Anti has an N in it, so that side where you will observe when you bring that side of the solenoid in front of you, if you see that the current is flowing in an anti-clockwise manner, so that side will be the north pole. And if you bring a side or an end of the solenoid in front of your face, and you observe that the current is flowing in a clockwise manner, then that end of the solenoid will be the south pole. So these are the two ways in which you can tell that the solenoids, which side will be which pole. So here we have found that this side will be the north, this side will be the south. So from this north, the magnetic lines will be coming out, and they will be going into the south. I hope that you have understood this. It was a 2-mark question. Okay. The B part is figure 7.2 shows a beam of beta particles in a vacuum passing into a magnetic field. So here we have beta particles, and you know the beta particles are negative electrons. So they are negative charges. And here we have a magnetic field is out of the page. So the magnetic field is coming out of the page. Okay. So the movement of beta particles from left to right is an electric current. It's not a conventional current, it's electric current. On figure 7.2, draw an arrow to show the direction of the conventional current. So the electron current is going in this way, electric current is going from left to right. The conventional current will be opposite to it. It will be towards left. So draw arrow like this. Then he says a solenoid is used to produce a magnetic field that lies within the shaded region. On figure 7.2, the direction of the field is out of the page. On figure 7.2, draw the path followed by one of the beta particles in the shaded region. It's a 2-mark question. Okay. So here, when the beta particles will enter in this magnetic field, we can find the direction of the deflection. We will use the left-hand rule. Left-hand rule is very simple. You take your left hand, and this is your left hand. I'm saying the left hand. Okay, stretch the fingers in such a way. You can see that these 3 fingers, the thumb, the index finger, and the middle finger, they are perpendicular to each other. You can see they are perpendicular to each other. So this is called F. You see, this is called F. Thumb is called F. This is called M, and this is called C. F, M, C. The thumb is F. The thumb is F, force. The M is the magnetic field, and C is the current. So the magnetic field is out of the page. The current is going in this way. So see, I'm applying, I have to twist my hand. The magnetic field is out of the page, and the current is going to the right side. My thumb is pointing downward. So, but there is a problem. So the left hander told me that this should go downward, but there is a problem. The left hand rule is not for the negative charges. The left hand rule is for positive charges. So when I applied the left hand rule, the thumb was pointing downward. It means the beta particles means the charges should go downward, but that law is not for the negative charges. So the negative charges will bend or deflect in the opposite direction. So what will happen here? The beta particles will be deflected upward. I have done this on a paper also. Let me show you my work, and also let's read the last part. The direction of the current in the solenoid is reversed. State what happens to the path of the beta particles. Okay, we will discuss this also. You see here, you can see these are the beta particles. This is the direction of the conventional current. Electric current is going from left to right. The conventional current will be from the right to left. So beta particles enter into this magnetic field. The magnetic field is represented with dots. Dots mean that the magnetic field is coming out of the page. So the beta particles entered here by applying the left hand rule. We found the direction of the deflection of the beta particles. You know that left hand rule told us that the charged particles should bend downward, but we know that the left hand rule is for positive charges. Beta particles are negative charges. So we choose an upward direction, opposite to what the left hand rule has told us. So the beta particles will be deflected in the upward direction. So the last part was that if the direction of the current is reversed, what will happen? The beta particles will be deflected towards the bottom. If you change the direction of the magnetic field, if you change the direction of the magnetic field here, if the magnetic field is now into the page, represented with the crosses, the beta particles deflection will be opposite. Now this time, before the beta particles bending upward, now the beta particles will bend towards the bottom of the page. The beta particles will bend towards the bottom of the page. A 600 ohm resistor and a thermistor are connected in series with an ammeter and a 20-volt DC direct current power supply. A voltmeter is in parallel with the resistor. The ammeter reads 0.025 amp. Calculate the reading on the voltmeter. Okay. So the current coming from here is 0.025 amp. It means that the current flowing here is 0.025 because there is a single loop. These two resistors, they are connected in series with each other. So the current will have a single path. The current coming from the battery will flow through this. The same current flow through the ammeter. The same current flows through the 600 ohm resistor, and the same current will flow through the thermistor and come back to the battery. So the current flowing through the 600 ohm resistor is 0.025 amp. So if I know the resistance of this thing, 600 ohm, and if I know the current flowing through this, so we know that the V is equals to IR. V is equals to IR. So I can calculate the voltage drop. V is equals to IR. The I is 0.025 amp, and the value of the resistance is how much? The value of the resistance is 600 ohm. So by doing the calculation, you can calculate the voltage drop, and the answer will be 15 volt. I have done this on a paper. Let me show you my work. So here, I know the current flowing through the 600 ohm resistor, so I can calculate the voltage drop. V is equals to IR, 0.025 amp multiply 600, and the answer is 15 volt. I hope you have understood. The next question is the resistance of the thermistor. The resistance of the thermistor. The resistance of this thermistor is question, and we just calculated that the voltage drop here are 15 volt. You know the current is coming is 0.025. So the current flowing through the thermistor is also 0.0. 0.025 amp. I know the current flowing through the thermistor, that's 0.025 amp. The battery voltage or EMF of the battery is 20 volt. 15 volt is taken by this R1. So how much voltage is left for this? The total voltage of or the EMF of the battery is 20 volt. If the 15 volt is taken here, here you will have only 5 volt. So you see now I know the voltage drop here 5 volt, and I know the current flowing through here that 0.025. So I can calculate the resistance of the thermistor. B is equals to IR. So R is equals to V divided by I. R is equals to V divided by I. So 5 divided by 0.025, and the answer will be 200 ohm. Let me show you my work. I've done this on a paper also. So the V2, the voltage drop across the thermistor will be equals to the voltage of the battery minus the voltage taken by the 6 ohm resistor. So 20 minus 15, so 5 volt. So the voltage drop across the thermistor is 5 volt. The current flowing through the resistor, we know that 0.025 amp. So apply the formula that V2 is equals to IR2. R2 is equals to V2 divided by I. 5 divided by 0.025, and the answer will be 200 ohm. I hope that you have understood this numerical. It was a 2 marks numerical. Then he says the temperature of the thermistor increases. State what if anything happens to the resistance of the thermistor. You know, thermistor is a non-ohmic conductor, and its resistance depends upon the temperature. If you will increase the temperature of the thermistor, its resistance will decrease. The resistance of the thermistor will decrease. It's a 1 mark question. You only have to state the ammeter reading and to the voltmeter reading. You know, the ammeter, because if the thermistor reading drops, the total resistance of the circuit will drop. If the resistance of the thermistor decreases, you know, the total resistance of the circuit will decrease. So the current coming off the battery from the battery will increase. So the reading on the ammeter will increase because the resistance of the thermistor has dropped. So the thermistor will take less voltage. Now the voltmeter was connected across the 600 fixed resistor, 600 ohm resistor. The reading on the voltmeter will increase because the thermistor resistance has dropped. So the thermistor will take less voltage, it will consume less voltage. There will be less voltage drop across the thermistor. So the voltage drop across the 6 ohm resistor should increase. I've written this answer also. Resistance of the thermistor will increase. And the second part, ammeter reading will increase. And the voltmeter reading, the voltmeter was across the fixed resistor. That reading will increase. So my dear students, by this question, we have reached the end of this section A of this paper. Section B of this paper, we will attempt in another video. Dear students, today we have done October-November 2012 2-1 paper, and it's a theory paper. The course we are studying is Physics 5054, and today we have only done section A of this paper. Section B of this paper we will do in another video. My name is Ferhan Mazher, and I hope that these videos are useful to you and they are helping you to study very efficiently and prepare for your Cambridge exams and while sitting in your homes, and they will help you to improve your grades. Thank you very much, everybody. Have a good day and God bless you all. Thank you very much.